we introduce SEAT, Scene Editing as Teleoperation. Studies in robot teleoperation have been centered around action specifications, from continuous joint control to discrete end-effector pose control. However, these robot-centric interfaces often require skilled operators with extensive robotics expertise. To make teleoperation accessible to non-expert users, we propose the framework Scene Editing as Teleoperation that transforms the traditional robot-centric interface into a scene-centric interface. Instead of controlling the robot, users focus on specifying the task's goals by manipulating digital twins of the real-world objects, making the system intuitive, robust to network latency, and agnostic to robot hardware. In this project, we apply SEAT to the 6-off kit assembly task. Despite kit assembly being ubiquitous in the packaging and transport industry, most kitting operations are done manually. Here is the system in action. The camera first captures a depth image of the workspace. Then our scene completion algorithm translates the real-world workspace into a virtual scene. The user then specifies target object pose by editing the virtual scene using a browser-based 3D UI. After the user uploads the scene, our action snapping algorithm refines the provided user pose to improve the object kit alignment. Finally, the system computes and executes the actions to assemble the objects. In building the system, our first challenge is to translate the real-world workspace filled with novel objects into an editable virtual scene. As traditional pose estimation algorithms cannot generalize to unknown objects or categories, to tackle this challenge, we introduce a category-agnostic scene completion algorithm that segments and completes the real-world objects into a virtual editable scene representation. Our second challenge is to translate imprecise user edits to real-world robot actions which require accurate 6-off poses for successful kitting. We propose a shape-informed action snapping algorithm, which we refer to as SnapNet, that automatically corrects user imprecise inputs. Here are the details about SnapNet. Given an imprecise user input, SnapNet first performs a position refinement using deep convolutional neural networks. SnapNet uses the dense feature volume of the object as the kernel to perform 3D cross-convolution on the dense feature volume of the kit to obtain a predicted score for each 3D position. For the rotation refinement, SnapNet samples rotations in the search space, rotates the object point cloud according to each rotation before concatenating onto the kit point cloud, and finally passes the concatenated point clouds to a pointnet++ encoder to obtain a predicted score. To train SnapNet, we generated a large-scale kit assembly dataset, Kit 1000, that contains a diverse set of procedurally generated object kit pairs that mimic real-world kitting tasks. Now we show some quantitative results of SnapNet in both with user input and without user input scenarios. We find SnapNet to outperform previous baselines, KitNet and TransporterNet. By comparing with SnapNet trained and tested on partial volumes, we find that our scene completion algorithm to be essential to pose prediction. We also find SnapNet to be robust against errors in user input. On the left, as user error position increases, SnapNet maintains its low prediction error. Moreover, even with large rotational error, SnapNet can predict position with low error. Similar results are found for predicted rotation on the right. Now we show some qualitative results. Given an input observation, our scene completion algorithm first transforms it into a virtual scene. Then with some imprecise poses, SnapNet finds the correct 6-off poses. We also show the ground truth as a comparison. To evaluate SEAT, we conduct a user study with users that are inexperienced with our system. In SEAT on the left, the user specifies the goal poses of all objects at once. In the baseline system, EE control on the right, users specify the end-effector pose of the robot to move one object at a time. We first show a trial with 2 objects. Now the user finishes specifying the task goals in seat. Now seat successfully kits both objects. We now show a trial with 3 objects. Now users finish specifying the task goals in seat. Now seat successfully kits all 3 objects. We can see that the object slides in for E control even though the place pose is initially incorrect. Now we show the analysis of user study results. We have 3 objective measurements: success rate, user specification time, and execution time. For execution time, seat spent 12 seconds more per object than E control due to model inference time. For success rate and specification time, we group results by users and by trials respectively. We hypothesize significant differences for both measures, and the results of pairwise t-tests find that seat achieves significantly higher success rate with users spending significantly less specification time. We also have a subjective measure, the NASA Task Load Index, which consists of 6 user-reported components. Lower values indicate less task load. We hypothesized significant differences in all 6 components, and pairwise t-tests find that users experience significantly lower mental demand, temporal demand, effort, and frustration. Finally, we've also done experiments with real-world kits. Thank you very much for watching.